Engineers once packed the Holland tunnel full of running cars and deliberately let the air turn deadly, on purpose, just to find out exactly how much poison a person could survive breathing. That experiment happened because Thomas Edison, one of the most famous inventors alive at the time, said this project couldn't be done. Not wouldn't, couldn't. No ventilation system on Earth, he argued, could keep drivers alive inside a tunnel this long, packed with idling car exhaust. Most people call it the first underwater tunnel in the world. It wasn't, not even close. Underwater tunnels had existed for railroads for decades. What it actually became was something harder to pull off. The first underwater tunnel, engineered specifically to keep car exhaust from killing everyone inside it. I dug through original Engineering Society records, university research archives, and construction reports filed by the agencies that actually built it, then used AI to reconstruct the whole project in order, from the first survey to opening day. 2 chief engineers died before a single car ever drove through. 84 fans ended up running underneath the Hudson River to keep the next ones alive. Here's how they got there. The only way across the Hudson River between Manhattan and New Jersey was by ferry, a slow, weather-dependent system straining under the weight of a rapidly growing number of automobiles. Engineers weighed a bridge against a tunnel and picked the tunnel, partly on cost, and partly because a bridge tall enough to clear shipping traffic would have required enormously long approach ramps on both crowded shorelines. A 1913 cost estimate put the tunnel at roughly $10 million against $50 million for a comparable bridge, though the final tunnel bill would end up far past that early guess by the time everything was finished. On June 15, 1919, commissioners appointed 36-year-old Clifford Holland chief engineer of what officials were then calling the Hudson River Vehicular Tunnel. Holland wasn't a newcomer to this kind of work. He'd already spent years directing construction on 4 separate subway tunnels under the East River, a project worth $26 million in its own right. Nothing he'd built before came close to the scale of this one. He'd spent the years before that climbing steadily through the ranks of New York's Public Service Commission, from assistant engineer in 1906 up to division engineer by 1916. It was a slow, methodical rise through exactly the kind of underwater construction work this new project would demand, at a scale nobody had attempted yet. Underwater tunnels themselves weren't new. Railroads had been running trains beneath rivers for decades by this point. The problem nobody had solved yet was ventilation for cars. A train tunnel could rely on the locomotive's own momentum and a relatively brief transit time to get away with fairly primitive airflow. A road tunnel carrying idling, stop-and-go traffic for 1.5 miles straight was a different problem entirely. Carbon monoxide from thousands of gasoline engines would simply accumulate in an enclosed tube with nowhere to go. Nobody had ever needed to solve this exact problem before, simply because nobody had ever tried running this much continuous automobile traffic through a tunnel this long. The traditional solution, used in railroad tunnels for generations, pushed air longitudinally from one end straight through to the other. Engineers calculated that clearing exhaust out of a tunnel this long, using that method would require wind speeds over 70 miles an hour, blowing continuously through the tube. Applying that same logic to a road tunnel wasn't a minor miscalculation waiting to happen. It was a structural dead end, the kind of math that told engineers outright their existing playbook simply didn't work here. That's not a ventilation system. That's a controlled hurricane aimed directly at drivers. Could any ventilation system actually keep 1.5 miles of trapped car exhaust from turning lethal? Or was Edison right to doubt it? I love the irony of Thomas Edison, of all people, being the public skeptic on whether this tunnel could ever be made safe to breathe inside. Solving it fell largely to engineer Ole Singstad, who proposed something nobody had tried at this scale, ventilating the tunnel transversely instead of end to end. Fresh air would pump in continuously through a duct running beneath the roadway. Exhaust would pull out continuously through a separate duct near the ceiling along the entire length of the tube. Singstad wasn't chasing a marginal improvement on the old method either. He was proposing to throw out end-to-end airflow entirely and replace it with something closer to a building's mechanical ventilation system, scaled up to tunnel size. A theory this untested needed more than confidence behind it. It needed proof nobody could argue with. Before anyone trusted that idea with actual drivers, engineers needed real data, not theory. The project brought in 3 separate institutions to solve 3 separate pieces of the same problem. The U.S. Bureau of Mines, working out of Pittsburgh, analyzed exactly what came out of a typical automobile tailpipe. Researchers at Yale determined how much carbon monoxide a human body could tolerate before real danger set in, settling on a maximum safe concentration of 4 parts per 10,000. That number wasn't a rough guess either. It came from controlled exposure tests that found the exact point where carbon monoxide started measurably impairing a person, then built in a safety margin below it. Engineers at the University of Illinois took that data and calculated how much airflow an actual ventilation system would need to produce to stay under that threshold. To test the theory for real, Holland's team built a test tunnel inside the Bureau of Mines experimental mine at Brewston, Pennsylvania. Then they lined up real automobiles with engines running and measured exactly how fast the air turned dangerous. The Brewston tunnel ran roughly 400 feet long enough to approximate real traffic conditions rather than a single isolated car. That let researchers measure how exhaust actually built up and moved through a confined space over time, rather than in a single instant. I still find it wild that the safety standard protecting millions of future drivers came from cars idling inside a coal mine, run specifically until the air got dangerous enough to measure. That data gave engineers exact numbers to design around instead of a guess. It also proved Edison wrong, on paper, before a single fan had even been built. With ventilation theoretically solved, crews could finally start digging. On March 29, 1922, officials awarded the tunneling contract to Booth and Flynn Limited for $19.3 million, part of a project that would eventually cost $48.5 million in total. Work on the actual tubes began within days, starting with an air compressor plant at the corner of Canal and West Streets on the Manhattan side. 3 companies had bid on the job, and officials went with the lowest offer rather than negotiating further, a decision that put enormous pressure on Booth and Flynn to hit both budget and schedule from day one. Crews dug 2 separate tubes using the same shield method proven on earlier underwater tunnels. A massive circular steel shield pushed forward through the riverbed, while workers excavated the exposed face and lined the tunnel behind them with cast iron rings bolted together, section by section. Compressed air inside the work chamber kept river water and mud from collapsing the tunnel before the lining could go in, reaching pressures up to 47.5 pounds per square inch at the deepest points. Workers, nicknamed sandhogs, entered and exited through airlocks and could only stay inside the pressurized chamber for strictly limited shifts before the physical toll became dangerous. Fires were a constant secondary risk inside those pressurized chambers too, since compressed air fed flames far more aggressively than normal atmosphere, forcing crews to work with extra caution around anything that could spark. How do you keep 2 separate tunnel crews boring toward each other from opposite riverbanks, from missing each other completely underwater? Constant resurveying, mostly. Engineers rechecked alignment repeatedly as each shield advanced, since a navigation error compounding over more than a mile of blind digging could have left the 2 bores meeting at the wrong depth, or missing each other in the dark entirely. Surveyors used triangulation from fixed points on both shorelines to check the shield's position at regular intervals. It was essentially cross-checking an underwater, invisible process against measurements taken entirely above the water's surface. By October 1924, after 5 years of non-stop pressure, the 2 headings of the tunnel were finally days away from meeting. Clifford Holland never got to see it happen. The stress of running a project this size on this deadline had been building on him for years. So much rode on ventilation numbers nobody had proven at this scale before, and Holland felt every bit of that weight. That October, Holland suffered a nervous breakdown and retreated to a sanatorium in Battle Creek, Michigan, on doctor's orders. 2 weeks later, his heart failed. He died on October 27, 1924, 1 or 2 days before the tunnel's 2 headings actually connected. He was 41 years old. I can't get past the fact that Holland missed the single moment his entire career had been building toward by a matter of hours, not years. Less than a month later, the Interstate Tunnel Commissions voted to rename the project the Holland Tunnel in his honor, 3 years before a single driver would ever use it. His successor, Milton Freeman, took over as chief engineer almost immediately. Freeman lasted only a few months in the role before dying of acute pneumonia in March 1925. Freeman inherited a project already carrying the weight of one death, and had barely settled into the role before his own health gave out under many of the same pressures. Leadership finally landed on Ole Singstad, the engineer who'd designed the ventilation system in the first place. Singstad spent the next 2.5 years overseeing both the remaining tunnel work and the construction of the ventilation system his own research had made possible. Building that system meant constructing 4 separate ventilation towers, 2 anchored on land and 2 built out in the river itself. Norwegian architect Erling Oer designed them. Inside those towers, crews installed 84 fans total. Combined, they pushed roughly 3.5 million cubic feet of fresh air into the tunnel every single minute, fast enough to fully replace the air inside every 90 seconds. 2 of those towers sat directly in the river itself, built on their own artificial islands rather than solid ground. Crews had to solve a smaller version of the exact same underwater construction problem all over again, just to give the fans somewhere to stand. 84 industrial fans running underneath a live river. What happens to the air inside if even a handful of them go down at once? Only 56 of those fans needed to run at any given moment to keep the air safe. The other 28 sat in reserve, ready to compensate automatically if traffic volume spiked or a section of duct underperformed. Engineers deliberately overbuilt the whole system rather than sizing it exactly to projected traffic. They were betting that automobile volume would keep climbing long after the tunnel opened, and the ventilation would need headroom it didn't yet need on day 1. Something about 84 industrial fans running under a river just so people could breathe normally inside their own cars still strikes me as one of the most unglamorous, essential engineering solutions in this entire story. Getting that many industrial fans installed and synchronized inside towers still under construction meant electricians and mechanical crews working in the same confined spaces as the ironworkers finishing the tower shells around them. 2 very different trades, competing for the same limited square footage. Every completed section of duct had to be pressure tested before crews sealed it behind finished concrete, since a leak discovered after the fact would have meant tearing into a completed structure to fix airflow nobody could see from the roadway. Each tower also needed its own dedicated control room. Operators there could monitor airflow and switch additional fans on manually if sensors detected carbon monoxide levels creeping toward the danger threshold Yale's researchers had defined years earlier. By 1927, both tubes were finished. The north tube ran 8,558 feet. The south tube 8,371 feet, each one 29.5 feet in diameter. The roadway inside ran 20 feet wide, carrying 2 lanes of traffic at a maximum depth of roughly 93 feet below the river's high water mark. Finishing the interior meant lining both tubes with white ceramic tile below the ventilation ducts. Crews chose that tile specifically because it reflected what artificial light there was and made the tube feel less like a raw industrial shaft. Roughly 20,000 people walked the finished tunnel on foot during a public preview before it ever opened to a single car. That preview crowd moved through in a tightly managed 2-hour window, walking the full length of a tube that had taken the better part of a decade and 2 men's lives to finish. The tunnel formally opened to vehicles at midnight on November 13, 1927. Earlier that day, President Calvin Coolidge, aboard his yacht on the Potomac River, used a golden telegraph key to trigger flags unfurling at both tunnel entrances simultaneously. It was the same ceremonial key that had been used years earlier to detonate the final blast completing the Panama Canal. The first car to actually drive through from the Manhattan side carried the commission chairman alongside the widows of Clifford Holland and Milton Freeman. The tunnel's New York entrance plaza was named Freeman Square, after the second chief engineer, in the same spirit that had already renamed the whole tunnel after the first. None of the ventilation system was ever meant to be visible from inside a moving car. Drivers crossing under the Hudson had no reason to think about airflow, fan horsepower, or carbon monoxide thresholds tested in a Pennsylvania coal mine years earlier. That invisibility was the entire design goal. A ventilation system drivers never had to think about was, by definition, one that was actually working. That was exactly what Singstad, Holland, and Freeman had spent years trying to prove it could do. What all of this construction actually proves, in the end, is that the hardest problem here was never digging the hole. Tunneling under a river was already a solved engineering problem by 1920. What nobody had solved was keeping people alive inside a road tunnel this long. That took 2 research universities, a government mines bureau, an underground test tunnel, and the deaths of 2 chief engineers before anyone finally got it right. The same transverse ventilation principle Singstad proved here still runs under the Hudson today. It got a real-world test in 1949 when a truck fire inside the tunnel reached temperatures over 4,000 degrees. The system kept working, and the tunnel reopened within 56 hours. If you want to see the engineering up close, the ventilation towers on both riverbanks are still standing and still visible from the street today. Subscribe if you want more infrastructure broken down piece by piece like this. And tell me in the comments which tunnel or bridge I should dig into next.